In this video, we're going to discuss the very first integration technique that most students learn. Outside of just finding the indefinite integral for known derivatives, we can also use what's called substitution. Some books refer to this as U-Substitution, simply because U is usually the selected letter to substitute into the problem. Any letter will do. It's just tradition to use U and V as well. So the rules for this substitution is, first of all, you have to know your derivative forms. This technique relies a lot on pattern recognition. If you can't see what to substitute in or where it might lead you, this is going to be a very, very difficult route for you. And so you want to know your derivatives very, very well, especially the polynomial and the trig functions. These are the things that you're going to need to know the most, because these are the most common in at least for first semester calculus. Later on in first semester calculus, towards the very end, students typically will get into the exponential functions as well as the logarithmic functions, and dealing with powers on x of -1, which is an inverse and deals with the log, and we're not going to get into that in this video. However, these are the basic functions that we deal with in beginning calculus, and so you really, really need to be able to recognize these patterns. Okay, the second thing you're going to do is you're going to scan all the different inside functions for candidates. And I like the word inside functions rather than the embedded functions or the composite functions. Okay, so in this too, what would this look like? Well, let's just throw an example up here. Okay, and so we have something that looks like this. We have the integral of pi sine of pi x dx. Okay, so now you might think, well, what inner function could you possibly be talking about? Okay, sine is its own function, but inside it has another input function, and that function happens to be pi x. If you notice, pi x has a derivative of pi, and oh look, here's pi. Okay, so already we're talking about rules 1 and 2. You have to know your derivatives, particularly of polynomials and trig functions, and you have to be able to recognize them. 2, scan the different inside functions. Very often your substitutions will come from the inside. They can also come in the form of product functions, as I will give you an example here in a bit. Okay, so now they will have the derivatives that are on the outside of the chosen function, as pi is on the outside of the function that we were talking about. All right, now we are going to substitute u for the inner function found in step 2. So for that inner function, we're going to simply let u equal pi x. That's it. That's the substitution part. It's not really that bad, is it? Okay, but now in step 4, find du in terms of the variable being substituted. In other words, you're going to take the derivative and find the differential du and see what that version is. It's very, very closely related to related rates. How does u change as x changes, that sort of thing. And so for this particular example, then we have, if we take the derivative of both sides, du with respect to x is equal to simply pi. But now we don't want that. We actually want to get rid of dx as well. And so this is going to become du, if we multiply both sides by dx, it's going to be, not that, pi dx. In other words, wherever we see a u, we can put or wherever we see pi x, we can put u. Wherever we see a pi dx, we can put du. This is the trick to the substitution. In order to make an effective substitution, you must be able to rewrite dx as du. I can't stress this enough. This is imperative. Sometimes you will simply have to make it appear by using the constant, the ability to pull out a constant in an integral you can effectively multiply and divide by the same thing and it doesn't change the value. And I'll show you that technique as well. Okay, step 5. When dealing with definite integrals, you can do one of two things. I've tried changing the limits, but very often I will simply do the substitution, bring it back in as an indefinite integral. The answer then is just take that indefinite integral and evaluate it at the lower and upper limits in the original integral. Okay, and so what I'll do is I'll make the substitution, perform the integral, go back and re-substitute my x's or my values of back into u. And so in this case, I would put u back into pi x. So anywhere where I had a u in this, I would put u back into pi x. Then I would use my original limits of integration. Now, if you choose not to go that route and you keep everything in u's, that's fine. But you have to recompute the limits of integration given your substitution. Okay, you have to use your substitution. So if we're going from 0 to 2 pi, for example, in this particular example, I would have to put x is equal to 0 and find out what u would be, and that would be u equals 0, and then x equals 2 pi, in which u would equal to 2 pi squared. Okay, now that changes the limits a little bit. And so when you make these substitutions, you will be changing those limits. Again, you can choose whether to substitute, integrate, and then unsubstitute effectively, then evaluate, or you can substitute, find new integration limits, and then continue with that definite integral as you would any other. And finally, you may need to not only use a u to x substitution, which means define u as some function of x. You also may have to do a simultaneous x to u substitution. Meaning you might have to find, if we wanted to find x in terms of u, this would turn back into u over pi is equal to x. We might have to do that simultaneously. I'll be giving you plenty of examples of all of these different types of tricks, if you will. They're not really tricks. They are proven techniques, but very often mathematicians make a good guess and then go back and prove that their guess must be. Okay, so now let's go ahead and finish up with this particular example. Now I've made my u substitution, and so let me go ahead and rewrite this here. We have the integral of pi sine pi x dx. Okay, so now we've made our u substitution of u is equal to pi x. If we take du, then du is equal to the derivative of pi x, which is pi, times dx. Again, this is something that you take the derivative, then multiply by dx. Eventually, you'll practice enough. Well, you just do it. Just rewrite the differential. Okay, now that we do that, let's go ahead and convert everything then. Wherever I see, and I'm going to change this to blue, wherever I see a pi x, I put a u. So I have a sine of u. Now, here's the trick. Wherever I see pi dx, I put a du. So now I'm integrating sine of u du. But the integral of sine is just negative cosine. So that's negative cosine of u plus c. So now what we can do is we can say, oh, okay, well, u then is my pi x, and so this is really negative cosine of pi x plus c. Okay, and so now you can check that through differentiation, and if you differentiate that, then the derivative with respect to x of negative cosine pi x is equal to, and this becomes the negative of sine pi of x times the derivative of what's inside, which is pi, and when you differentiate plus c, it becomes 0, and oh look, whoops, derivative of cosine is negative sine, the two negatives cancel out. Okay, And that's exactly what our integrand was. And so that right there is just a quick way to check. Let's try some other examples in the next video.